In this section, we're going to cover conic sections, and we're going to cover it more as a crash course to get you ready for the basics that you'll need to know when we start dealing with multivariable functions and graphing surfaces. It's going to be really helpful if we know how to quickly identify and graph a conic section. Right? So a conic section is a quadratic equation in two variables. So it has a form ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Okay, it can be written in this form, where of course a, b, c, d, e, and f are just constant values. Now, this xy term makes things kind of complicated. It rotates the conic section, so we're going to ignore it. We're going to assume that b is equal to 0, and we're going to just focus on what happens when we have the rest of this here, okay? We're mostly going to be interested in what A and C are doing. That's going to tell us what kind of conic section we're dealing with, all right? Now, these are called conic sections because they are sections of a cone. So right here, I have a double-sided cone. And what we're going to do is we're going to look at what happens when I intersect a plane with that cone. Now, in this case, I have a horizontal plane, and the intersection is a circle. So a circle is a kind of conic section, okay? Now, if I rotate that plane, I get an ellipse, kind of a squashed circle, right? That's another kind of conic section. If I keep on rotating it until the plane is parallel to the slope of the edge of the cone, then I end up with a parabola. And if I keep on going even further, then I end up with a hyperbola, which is this two-sided structure. Now, there are other structures that are possible, but these are the basics that we are going to cover. The first kind of conic section we're going to dive into is a parabola. You're probably familiar with this kind of conic section. So let's look at an example of a basic parabola. So one example of a parabola is y equals some constant, let's say 2, times x squared. Okay, so in this case, it does follow this form, right? We have an x squared term, so a is equal to 2 in this case. Okay. Cy squared, gone away. So a parabola only has one of these guys that are squared. The other guy vanishes, right? And then we do have a y term in this example. These guys are 0. Okay. So how do you graph a parabola? Well, you're probably familiar with how to graph a parabola. Okay. Parabola has a vertex. In this case, the vertex is at the origin. Okay. And then if we go 1 unit to either side, if the x is 1 or -1, that gets squared. And then the y becomes 2. So this tells you if you go 1 unit away from the vertex, how far up are you going? Okay, so 1 unit away, I'm going up 2. So if I go up 1, or if I go to the right 1, I go up 2. If I go left 1, I go up 2. Okay, and we get this sort of U shape. Okay, so this number here tells you if you go 1 unit out from the vertex, how far up are you going? If that number is negative, then it will go down instead, right? So here I still have a vertex at 0, 0. Here's my vertex at the origin. Okay. And then if I go 1 unit to the left or to the right of that vertex, I'm going to go, in this case, since it's negative, down 1/2 unit. So 1 unit to the right, I go 1/2 a unit down. 1 unit left, I go 1/2 a unit down. And I get a sort of U shape. Okay, so you could see that this number in front determines whether you're opening up or opening down, and also determines how wide or skinny your parabola is. If it's a bigger number, then going left or right 1, you go up faster, right? So you get a skinnier parabola. If it's a number less than 1, then when you go left or right, you don't move as much. In this case, I'm going down only 1/2 when I go left 1 or right 1. Okay. And because I'm not going down as much, it opens slower. It's a fatter parabola. Okay. So in both these examples, I have y equals some number times x squared. But another kind of parabola is a sideways parabola. This will happen if instead of the x being the squared guy that I keep, if I keep the y squared. Okay? If I keep the y squared, I'll get something like x equals 3y squared. This is the exact same thing, except now because the y is squared and the x isn't, it opens in the x direction along the x-axis. So my vertex still is at the origin here. Okay. But now everything's on its side because x and y swap places. So now if I go up 1 unit or down 1 unit, I'm going to move in the positive x direction 3 units. Okay. 3 units, 3 units. So I get a pretty skinny parabola. Okay. And of course, if that coefficient in front of the y squared is negative, then it opens along the negative x-axis. Okay, so vertex at the origin. Now if I go 1 unit away from that vertex, up or down in this case, since it's opening to the left, I'm going to go -2 units in the x direction. So 2 units this way, 2 units this way. There's my parabola. Okay. Next, let's talk about circles. Now, the basic property of a circle is that it's the set of all points a set distance from a center point. So in this case, if we imagine that the center point is the origin, okay, there's my center, 0, 0. I want all the points a set distance away from that origin. In this case, let's say 2 units away. Okay, so this is the set of all points 2 units away from the origin. So with this definition, we can actually derive the equation of a circle, right? So if we take any point xy on the edge of this circle, okay, then we know by the Pythagorean theorem, we kind of inscribe a triangle here. This distance here is x, this distance here is y, and this distance here would be the radius, okay? Which in this example is 2. Okay, so if we use the Pythagorean theorem, we know x squared plus y squared is equal to the radius squared, okay? In this case, that'd be x squared plus y squared equals 2 squared, or x squared plus y squared equals 4. Okay, so this is a circle, and the key thing here is radius squared. Now, this is a particular example with the center at the origin. We'll deal with centers not at the origin a little bit later. Okay, but let's just do one example just so we can see. Let's graph this circle. X squared plus y squared equals 25 fourths. Okay? So the x squared plus y squared bit, that's telling us, hey, we got a circle here, and the center is the origin. Okay? The only thing that we need to identify here is, hey, what's the radius? Okay? Now remember, this is the radius squared. So the radius is going to be the square root of that, which is just 5/2. Okay. Notice we don't have to worry about a plus or minus because the radius represents a distance, right? It's the distance from the center to the edge. Normally, if you're taking a square root, you do have to think about that plus or minus. But in this case, we know radius is a distance. And so we want to use that specific interpretation. So we don't need a plus or minus. Okay. So we get our center at the origin. And then I'm just going to use my radius and count my radius left, right, up, down from that center point. Okay, so 5/2. So that's 1, 2, 3. So 5/2 would be, let's see, that's a half, 2/2, 3/2, 4/2, 5/2. Okay, so 5/2 is 2.5. If I go that distance in every direction, that gives me some points to base my circle on, and now all I have to do is connect the dots. So that circle is the graph of the equation. Notice I've drawn the center. That's not actually part of the graph. I just used it as a reference point. The graph is the circle here, right? This circle, that's the graph. Okay, and I should have pointed this out earlier, but do notice that this is a conic section. I've got a square term here, I've got a square term here, and then these two guys are 0, and then I've got a constant value here. Okay, notice one way that we identify this as a circle is if these two guys have the same value. If A and C are the same value, we're dealing with a circle. Assuming this isn't, this won't give you a negative value on the other side, then that's nothing. Okay. But if these two guys are the same value, if A and C are the same value, you have a circle. So next we're going to talk about ellipses. Now, a circle, which we just covered, is actually a special kind of ellipse. If you remember, a circle is x squared plus y squared equals r squared. That's a circle, right? Now, we could write this a different way. If we divide by the r squared, we get x squared over r squared plus y squared over r squared equals 1. This is also the equation of a circle. It's just a non-standard way to write that equation. Now, what we do for an ellipse is we take this and we just change the values of these so that they don't have to be the same. Okay? So for an ellipse, we take x squared over some number squared plus y squared over possibly a different number squared equals 1. This is the standard form of an ellipse centered at the origin. Okay, and again, notice that this is a conic section. We have an x squared term. We have a y squared term. Okay, notice that they're the same sign. Okay, a squared is always positive, b squared is always positive. So the number in front of the a squared and in front of the x squared and the y squared, the a and the c, are always going to be the same sign. If they're the same sign, you have an ellipse. Okay? Now, let's graph it. Ellipses are pretty straightforward to graph. So let's do x squared over 4 plus y squared over 9 equals 1. Okay. So again, center is at the origin. And what we want to do is we want to, just like with a circle, we want to plot the points that intersect the xy axes. What happens if you go left and right and up and down from your origin? Well, if I go left and right, that means my x is changing, but my y would be staying at 0, right? If I stay on the x-axis, my x would be changing, but my y is 0. So if the y is 0, this would go away. And then to make this equation true, x would have to be 2 or negative 2. So that x squared over 4 would be 1, right? So I take the square root of this and I go left or right that distance. Okay, so 2 to the right, 2 to the left. Okay, and then same thing going up and down. If I'm going up and down, my x would be 0, so that goes away. And then what makes this equation true? What makes y squared over 9 equals 1? Well, y could be 3 or y could be negative 3. So you always go up and down the square root of the denominator of your y term. Okay? So up 3, down 3. And then all we want is an ellipse that goes through all those points. Okay? And so they kind of, you just have to connect the dots after that, knowing that you're dealing with an ellipse. Okay? One more example, real quick. Let's not make it too hard. Let's do 9/4 plus y squared equals 1. Okay, so this one looks maybe a little different, but we're going to approach it essentially the same way. Okay, it is an ellipse. I have x squared, I have y squared, and they're both positive, right? So since they're the same sign, I'm dealing with an ellipse. Center is still at 0, 0, 0, the origin. In the x direction, the denominator here is 9/4. So I want to take the square root of that and go left and right in the x direction, the square root of 9/4, which is 3/2. Okay. So 3/2 is 1.5. So I'm going to go 1.5 units left and right. Now what about for the y? Y is squared, there's nothing in the denominator. Well, there's always a denominator. Sometimes it's just invisible, right? So it's an invisible 1. Square root of 1 is still 1. So in the y direction, I'm going to go up 1 and down 1. And then just connect the dots, which because I'm on a computer, I could do it in a fancy way, and I get my ellipse. The last type of conic section we are going to look at is hyperbolas. Okay, these ones are just a little more complicated than the others. So hyperbolas can come in a couple different forms depending on how they open, kind of like a parabola. Okay, they do have two squared terms like an ellipse. So this is one form of a parabola. This parabola has a center at the origin and it opens in the x direction. Okay, so center at the origin. Let me draw it with a different color. So we have our center at the origin, and then it opens in the x direction. Now, to figure out how to sketch this, you're going to start by creating a box using your A and your B. So just like with a hyperbola, you're going to move in the x direction, A units. You're going to move in the y direction, B units. Okay? So A units in the x direction, whatever that is, and then B units in the y direction. Okay? You want a couple points at all those locations. Okay? And then you're going to draw a box through those points. Kind of like this. Now notice it's a dotted line that I'm drawing because it's not actually part of the graph. This box is just a guide. Now what we want to do is we want to draw lines through the opposite corners of this box. Okay, so there's one line, and then through the other two opposite corners. Okay, so again, these are just guides. Those lines are my asymptotes. The further out you get, the closer the hyperbola is going to approach those asymptotes. Okay, now we do this no matter how the hyperbola opens. In this case, the x term is positive, so we're going to open in the x direction. So after drawing the box and knowing you'll open in the x direction, we're going to grab 2 points, our vertices of our hyperbola, okay, and we have 2 shapes opening up. We're going to have one shape opening this way in the x direction, since the x is the positive, and I approach those asymptotes. And then same thing opening in the other direction, in the negative x direction. Okay, so the blue is the actual hyperbola. All that, all the box and the asymptotes, those are just a guide. Okay, the hyperbola is this bit here and this bit here. Okay, let's look at another example, a more concrete example, and then we'll see what happens when we flip the role of x and y. So let's do x squared over 4 minus y squared over 9 equals 1. Okay? So this is a conic section because it's got the x squared and the y squared. It's a hyperbola because these guys are opposite signs. Notice the minus in the middle. Okay? The x squared term is positive, the y squared term is negative. And so that tells me I'm dealing with a hyperbola. Because the x is positive, with 1 on the other side, that means that this is going to open in the x direction. So I'm going to start by getting my center. This is a hyperbola centered at the origin. I'm going to move in the x direction the square root of 4 units. So 2 units in the x direction. So 1, 2, 1, 2. So 2 new units in the x. And in the y direction, up and down, I'm going to move 3 units from the origin because 3 is the square root of 9. So 1, 2, 3 units. 1, 2, 3 units. Okay? Draw a box through those 4 points. And then through the corners of the box, I draw my lines, my asymptotes. Okay, because this is opening in the x direction, I'm going to fill in these points right here. Those are the actual vertices of my hyperbola, and then open in the x direction. I'm just going to hug those asymptotes. It's a very wide opening hyperbola. Let's try that again. Okay, let's do one more, but now let's flip the role of x and y. So let's graph a hyperbola that looks like y squared over 4 minus x squared over, let's make it also 4, equals 1. Okay, again, how do I recognize it's a hyperbola? I got an x squared and a y squared, and they have opposite signs. The y squared term is positive, the x squared term is negative. Okay, centers at the origin. In this case, the denominator of both of these is 4, so I'm going to go in the x direction and the y direction 2 units. Right? So 2 units this way, 2 units this way, 2 units this way, 2 units this way. Okay? 2 units in the y direction, up and down, 2 units in the x direction, up and, left and right. Draw your box. Draw your asymptotes through opposite corners. And now in this case, the y is the positive. Because the y is positive, I'm going to open up and down. Okay, so these are my vertices. And then just draw out from the vertices, hugging your asymptotes. So notice you could identify a lot about these conic sections pretty quickly just by identifying information about the x squared and y squared terms. And that's going to be important going forward. Looking at this, even before graphing, I know, okay, I'm dealing with a hyperbola because I've got x squared and y squared, and they're opposite sides. And I know it's opening in the y direction. Okay, and a lot of times, having that in your mind will be enough once we start dealing with this in a multivariable setting. So far, we've only looked at conic sections with the vertex or the center of the conic section at the origin. Now we're going to look at conic sections where the vertex or center is not necessarily at the origin, where it's shifted. Okay, so we're going to start again with parabolas. And the general form of a parabola, where the conic section, where the vertex rather, is not at the origin, is something like this. X minus h squared plus k. So in this case, the y is the non-squared term. If we were to square this out, if we were to FOIL out x minus h squared, the x would be the squared term. Okay, so this is opening in the x direction. I'm sorry, in the y direction. It's opening either up or down. As before, the A tells you how fat and skinny you are, whether you're opening up or whether you're opening down, depending on whether that's A is positive or negative. It performs the exact same role as before. What's new, though, is this H and this K. Now, if you remember your graphing transformations, what these are going to do is it's going to shift the graph of the parabola. It's going to shift it h units to the right and k units up. And if you're looking at the vertex, which was at the origin, that means the origin moves, the vertex moves from the origin h units to the right and k units up. So the new vertex is hk. Right? Let's look at this in an example. Do a couple of examples with this. So let's do y equals 2, x minus 3 squared plus 1. Okay? So we're going to graph this just like we have done with other parabolas, but the minus 3, the plus 1, that's going to shift the parabola 3 units right, 1 unit up. So the new vertex is at 3, 1. So instead of being at 0, 0, it shifts 3 units right, 1 unit up. And so the new vertex is right here at 3, 1. Okay? And now we graph the rest of the parabola just as we did before. Okay? The number in front here is 2. So if I go left 1 or right 1, I'm going to go 2 up from that vertex. Okay? So left 1, 2 up. So left 1, 2 up. Right 1, 2 up. And this kind of gives me the 3 points I need to graph my parabola. Okay? Let's do one more example. But let's open in the other direction this time. Let's have an x equals parabola where the y is the squared term. Okay. We have x equals negative 3, y minus 2 squared plus 3. We will be opening in the x direction. Since the x doesn't have the square, the y does have the square. So we'll be opening left or right. Since this number in front is negative, that means it will be opening in the left direction, down the negative x-axis. Okay. Now, what's our vertex? So we shift like before, but notice this isn't an x anymore. So this isn't the vertex position associated with the x. It's the vertex position associated with the y. Okay. So my vertex is the x position of the vertex is 3, and the y position is 2. So notice that that's swapped from what we did up here. Okay. Here the vertex was 3, 1. This guy is associated with the x, this guy with the y. But down here, our x and y, the roles have flipped. So now this guy is associated with the y and this guy with the x. All right, so just be aware of that. Okay, so our vertex is 3, 2. So 1, 2, 3, 2. There's our vertex. And I know I'm going to open to the left. If I go 1 unit away from the vertex, in this case up or down, so 1 unit away from the vertex, my x changes by negative 3 units. So I'll go 1, 2, 3 units left, 1, 2, 3 units left. And so that gives me the information I need, the points I need for my parabola. So now just kind of connect the dots, draw a parabola. By the way, this parabola is a U-shaped, right? Sometimes students get lazy and draw a V-shape. It is not a V-shape. Okay, do not draw a V-shape. It's a U-shape. Next, let's deal with circles where the center is not at the origin. We're going to deal with this almost the same way as we dealt with parabolas. Okay. the form we learned for circles before is x squared plus y squared equals the radius squared. If we want to shift the center of the circle from the origin to some other center, we want x minus h squared plus y minus k squared equals r squared. So here the center is hk. And that kind of makes sense if you think about it, because when x is h and when y is k, that's playing the role as 0 did up here, right? When x is h, I get 0 squared here. H minus h is 0. If y is equal to k, k minus k is 0. So when x is h and y is k, I get 0 squared plus 0 squared, just like up here when x is 0 and y is 0. Okay? That's really the only big difference here. If we can identify this circle in standard form, if we can identify this as a circle and we can identify the center, then we can easily graph it. So let's do an example. X minus 2 squared plus y plus 1 squared equals 25. Okay, so this is a circle in standard form. First thing, let's identify the center. The center of this circle is not 0, 0. For x, we get 2, and for y, it's going to be negative 1, right? Because we could think about this as y minus negative 1 squared. Notice the negative in the formula for general form. So we want this to be negative 1. Another way to look at it is you want y, the value of y here, to make this expression 0. So when y is negative 1, negative 1 plus 1 is 0. Same thing over here. You want the x here so that this expression is 0. So when x is 2, 2 minus 2 is 0. Okay? The radius is square root of 25, which is 5 in this case. Okay? With center and the radius, it's now real easy to graph the circle. Plot the center of the circle. So it's at 2 on the x, negative 1 on the y. There's my center. And then from the center, I go out my radius in all directions. So 5 units in all directions. And I'll just go up, down, left, right to get 4 points in the cardinal directions. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I've gone 5 left, right, 5 up, down, and now I am ready for my circle. Now let's cover ellipses not centered at the origin. These are going to be very similar to circles. After all, circles are just special kinds of ellipses, right? So the standard form of an ellipse not centered at the origin, we just do the shift thing again. Instead of just x squared, it's x minus h squared. That shifts the center x or h units to the right over a squared plus y minus k squared. That minus k shifts the center k units up over b squared equals 1. This one is easy to forget about, but it's really important. If you do not have that 1 there, your equation is not in standard form. Now, so far, I've only given you examples where the equation is already in standard form, but eventually we'll get to the point where we will need to set the equation in standard form first before we can graph it. The equations of these conic sections are easiest to graph when they are in standard form. Okay, so for an ellipse, that 1, very important. Okay. So the center of this ellipse, just as with the circle, is at HK. And the same rule applies. you're choosing the x and y here so that these expressions are 0. Okay, so let's do an example. Let's graph the ellipse. Let's do x minus 2 squared over 9 plus y plus 1 squared equals 1. Okay? So we could quickly identify our center. My center is going to be 2, negative 1. 2 makes this guy 0, negative 1 makes this guy 0, right? And so let's graph it. So 2, negative 1, 2 out on the x, 1 down on the y. There's my center, 2, negative 1. In the x direction, I'm going to move left and right 3 units because 3 is the square root of 9. So from the center, 1, 2, 3 units. 1, 2, 3 units. Okay. And for y, well, again, y doesn't have a number here in the denominator, but there's always a number, right? It's an invisible 1. Square root of 1 is 1, so I'm going to go up and down 1 unit. So 1 unit up, 1 unit down. And those are the edges of my ellipse. So now I just have to draw an ellipse through those 4 points. And there is the graph of my ellipse. And finally, let's look at hyperbolas in standard form. This follows the same pattern as circles and ellipses. So we have x minus h squared over a squared minus y minus k squared over b squared equals 1. Just like with ellipses, that 1 is important. If that's not a 1, you have to rearrange your equation to get it to be a 1, so you're in standard form. We know it's a hyperbola because of the minus in the middle, right? The term with the x squared and the term with the y squared will have different signs. Okay, but we are shifting because of the minus h and the minus k. That shifts the graph over h units to the right, k units up, making the center of the hyperbola hk. Okay, now remember, hyperbolas, like parabolas, they can open different directions. This one, because the x is positive, the hyperbolas will open left and right along the x-axis. But if we swap it, so that the y is the positive and the x is the negative, now it opens in the y direction, right? Because now the y is the positive. But the center is still hk. Okay, this guy, the guy with the x, that tells us how far we shift left and right. The k, the guy with the y, that tells us how far we shift up and down. Okay, so let's do a couple of examples. So here we can identify this is a hyperbola because of the minus, the opposite signs of the x squared term and the y squared term. And we'll be shifting 1 unit right and 1 unit down. Our center is 1, negative 1. Positive 1, because positive 1 makes this 0. and -1 for the second term there, because -1 makes this guy 0. Okay, so let's start by graphing the center. 1, -1's right here. And I want to go 3 units left and right, because square root of 9 is 3. So 1, 2, 3 units right, 1, 2, 3 units left. I'm going to go 2 units up and down, because the square root of 4 is 2, and this is in the denominator of the y term, so I'm moving in the y direction, right? So 2 units up and down. 1, 2, 1, 2. Let's draw a box through those 4 points. Draw your asymptotes through opposite corners. Notice this box drawing step is exactly the same whether the hyperbola opens left and right or whether it opens up and down. It's not until after you draw the box that you have to identify which direction it's opening. In this case, it's opening in the x direction because that's the positive term. So I'm going to open in the x direction. So these two are the vertices of my 2 hyperbola halves. And draw so that you approach those asymptotes, hug those asymptotes. Okay. So there's an example of one opening in the x direction. Let's do another example with a hyperbola opening in the y direction. Okay, so let's do y plus 2 squared over 4 minus x squared over 25 equals 1. So again, we need to identify our center. Okay. Now the x squared term here is right here, but it's not in the form we're used to, right? We're used to x minus h squared. So what would be the h? Well, we could think about x squared as x minus 0 squared. Okay. Remember, you're looking for the x that makes this guy 0. That's going to be your x component of your center. Okay. So the x is 0 and the y is going to be -2, because when I plug -2 in for the y, it makes this term 0. Okay. So that gives me my center, and that's what I need to start. So 0, -2. I'm 0 on the x. I'm -2 on the y. So I'm going to go down to right here. That's 0, -2. Make it yellow. Okay. I'm going to go 4. So the denominator here is 4. So square root of 4 is 2. And because it's the denominator of the y term, I'm going to go in the y direction. So 2 units up and down. So 1, 2, 1, 2. And the denominator of the x squared term is 25. So I'm going to go square root of 25. That's 5 units left and right. Okay, so 1, 2, 3, 4, 5 units right. 1, 2, 3, 4, 5 units left. Draw your box around the center so that it goes through those 4 points. And then draw your asymptotes through opposite corners. Now, because the y term is the positive term, I'm opening in the y direction, up and down. So I'm going to draw from these points, those are my vertices. I'm going to hug the asymptotes. And hard to do when it's this wide. Close enough. Really wide opening hyperbola. So far, with all the conic sections we've looked at, we've always had an equation in standard form. So for example, maybe we have something like this. X minus 2 squared over 4 plus y plus 3 squared over 9 equals 1. Okay? Now this is an ellipse. It's in standard form, which makes it really easy to identify the important properties of the ellipse. I can look at this and I immediately know we're dealing with an ellipse. I know the center of the ellipse is 2, -3. I know I'm going to go 2 units out from the center left and right, and 3 units out from the center up and down. Right? I can quickly and easily graph that ellipse when I'm in standard form. But not all conic section equations have to be in standard form, right? What if I get something like this? 2x squared plus 4y squared plus 3x minus 2y minus 12 equals 0. Now this is also a conic section. It fits this form, but what kind of conic section is it, and what are the properties? Well, I actually can look at this and immediately know that we're dealing with an ellipse. Because if we look at our x squared term and our y squared term, they both have the same sign. So they are both positive. I will be getting an ellipse here. Okay, but I don't know what the center of the ellipse is. I don't know how far to go left and right or how far to go up and down from that center because it's not in standard form. I can't easily access the important information. What I want to be able to do is I want to be able to put it in a form kind of like this. Okay? And so I could kind of start to get there by pairing my x's together and pairing my y's together, moving the constant to the other side. Okay? But this isn't quite getting me there. I could get the 1 by dividing both sides by 12. And so we could start to see how we're getting there, but the crucial step I can't do yet. I want to convert both of these into something that's like x minus h squared, y minus k squared. A perfect square. And right now, they're not perfect squares. In order to get what we want, we actually need to turn them into perfect squares. In order to get this equation in standard form, we need to turn this and this into perfect squares so we could factor them like this. In order to do that, we need to complete a process called completing the square. Okay? The idea here is that we start off with something like this. X squared plus some term involving x, okay? And we want to add some magic value, let's call it c, so that this factors as a perfect square. Let's say x plus alpha squared. Okay? So the question is, what should c be to make this factoring work? Okay? Well, we could figure this out if we expand this side. If we FOIL out the right-hand side, that gives me x squared plus 2 alpha x plus alpha squared. And remember, we want that c. That c is the magic value that we need to know. We know what b is, okay? And we need to figure out c so that this factoring makes sense. Now, it turns out if you have two polynomials equal to each other, that means the coefficients of the same terms will also be equal. So for x squared, that's that's obvious, right? I get 1. 1 equals 1 from the x squared term. That's not very helpful. I already knew 1 was 1. But if we go for the x term, that means b must be equal to 2 times alpha. Okay, and because I know what b is, that tells me what alpha is. And if I go for my constant term, the term without any x's, it's on the left-hand side, it's c. That's what I'm looking for. And on the right-hand side, it's alpha squared. Okay, so what I can do is I can use this equation to figure out my alpha. My alpha is going to be b over 2. And I can use that and plug that in here. Since alpha is b over 2, that means my c is going to be b over 2 squared. So the magic number that I could plug in right there to make it factor like a perfect square is going to be half of this guy squared. Okay, let's look at this in a couple of examples. Complete the square. Okay, so we have x squared plus 8x plus some c. So what would c need to be to complete the square? Well, according to our work up here, it should be b over 2 squared, where b is the guy in front of the x. Okay, so my b here is this 8. Okay, so c is going to be b over 2 squared, which is 8 over 2 squared. That's going to be 16. So x squared plus 8x plus 16 should factor perfectly. And in fact, we could see that it will factor as x plus 4 squared. 4 times 4 is 16. 4 plus 4 is 8. Okay, so it does factor right. Notice, by the way, that this number here is always this number before you square it. Okay, I say that because it's not always as easy to factor as this guy is here. Okay, let's do a couple more examples. So let's complete the square. Okay, so I know based on what we've done already that the magic number c that's going to complete the square, that's going to let me factor this as a perfect square, is, well, c is going to be b over 2 squared. So that's 5 over 2 squared, which is 25 halves. Okay, so x squared plus 5x plus 25 halves. So with that as 25 halves, this now factors as a perfect square. So it'll factor as x plus something squared. But what's the something? Well, remember, it's always this guy before we square it. So it'll be 5 halves. And that's very useful here because this one would be a little bit trickier to look at and think about, oh, how does this factor, right? Because of this fraction, it would make it hard to factor. Okay, but by adding that 25 halves in, this trinomial now factors as a perfect square. Okay, let's do one more. Okay, we want to complete the square here. Now, this one's a little different because the guy in front of the x squared is not a 1. If you go back and look at our original work, we assumed that this guy in front was a 1. But that's easy enough to fix. If the number in front of x squared isn't 1, the very first thing we need to do is make it a 1. So what we're going to do is we're going to factor out that 2. Okay, so take out 2 from 2, get a 1. And all factoring out, that means I'm dividing. So 2 doesn't pull out evenly from 9. So I end up dividing by it 9 halves. Okay, and you could check if I distribute that 2 back in, I'll get this back, right? 2x squared minus 9x. Okay, now this guy inside has a coefficient of 1. So now I want to complete the square on this. So now I'm not going to worry about that 2 on the outside. I'm going to figure out what magic number C here is going to complete the square for me. Focusing on just this bit on the inside. That 2 is just hanging out on the outside. I don't have to worry about that. I'm just focusing on this where the leading coefficient's 1. Okay? So for this guy in here, my b is negative 9 halves. So my c, I know, is b over 2 squared. My b is 9 halves. Well, 9 halves divided by 2 is just 9/4. And if I square that, I get 81/16. Okay? And so the magic number that's going to allow me to complete the square here is 81/16. And that allows me to factor this as a perfect square. Not the 2, but that's okay. The 2 is easy to deal with. It's this part that we were worried about, the x's. Okay, so the 2 stays out here for the ride. But now this guy factors as a perfect square. And it factors as x plus this guy before we squared. And I actually made a mistake here. I'm just realizing it. My b, I wrote it as 9 halves, and it's not 9 halves. It's negative 9 halves. Now, when you square it, that really doesn't make a difference. It's still 81/16. But if I'm looking at this guy before we square it, that sign makes a difference. Okay? So before I square it, it's negative 9/4. And so this factors as 2 times x minus 9/4 squared. So we are going to use this technique to complete the square to turn our conic sections that are not in standard form into conic sections in standard form. Let's take a look at some examples of graphing conic sections that are not in standard form by first turning them into standard form by completing the square. Okay? So I have here a conic section. I want to graph it. So I need to put it in standard form. So first up, let's identify which conic section I'm dealing with here. You could do that by looking at the squared term. So I have a y squared, but I do not have an x squared. That means I'm dealing with a parabola, and a sideways parabola at that. If I have only the y squared, then I can get that x by itself on one side, put the y squared term on the other. I'm going to have a parabola on its side. Okay? So this is a horizontal parabola. And the standard form for a horizontal parabola is x equals some constant times y minus k squared plus h. If I can get it into this form, I can easily graph the parabola. So the trick is getting it into this form. Okay? So I'm going to start by doing what I can. I'm going to isolate the x in the equation. Okay? So I'm going to move everything else to the other side of the equation, leave negative 4x on the left side. And that's going to give me positive 12y squared plus 24y plus 24 on the right-hand side of the equation. And then let's divide everything by negative 4, get that x really by itself. So I get negative 3y squared minus 6y minus 6. Okay? All right. Now I've got the x by itself, but I do not have that y minus something squared that I need to put it in standard form. In order to do that, I need to complete the square. So what I want to do is I want to focus on just the y terms. The constant over here, I can deal with that. In the standard form, I have a constant all by itself. But it's these guys here that I have a problem with, right? All the y's that I have should live here. Okay? So let's just group those y terms together. Okay, all grouped together. Now I want to figure out how to turn this into a perfect square, right? I want to complete the square. Now, in order to do that, I need a coefficient of 1 in front. So first step, let's pull out that -3. Let's factor it out. So if I factor out the -3, I get a coefficient of 1 in front of the y squared. That's what I want. And pull out -3 from the -6. That leaves me with a +2 times the y. Okay? Now this is what I'm going to complete the square on. Okay? So what I need to do here is I need to figure out what magic number can I add right here to turn this into a perfect square. Okay? Now remember that number, let's call it c, is going to be b over 2 squared. In this case, my b is 2. So I get 2 over 2 squared, which is 1 squared, which is 1. Okay? So the magic number I want to add in here is a 1. There's a problem, though. Can I just add numbers into equation willy-nilly wherever I want as long as it's convenient? Of course not, right? I need to keep the equation balanced. I can't just add a 1 in there because I feel like it. So I need to offset it to keep it balanced, okay? So if I'm adding a 1, I also have to subtract a 1. Except, this isn't really a 1. If I were to distribute this -3 back in, what is it really? 1 times -3, it's a -3. This is really a -3, okay, that I've added to the right-hand side of the equation. So I need to balance that. So since this is really a -3, if I'm going to add in a -3, I also need to balance it by adding a +3. Okay? That way, if I were to distribute this and combine terms, the -3 and the +3, they cancel. Everything's nice and balanced, right? So remember that when completing the square, you need to keep the equation balanced. Whatever you add in, you need to subtract. Okay? Now, with this one here, that's the magic number. That's going to allow me to factor this as a perfect square. This one's simple enough that you could factor it without any help. Two numbers that multiply to 1 and add to 2, 1 and 1, right? So that's y plus 1 squared. Remember, this number is also always this guy before you square it also. Okay, and then over here, if I combine those two numbers, -6 plus 3, I get -3. And now this guy is in standard form. And now it's real easy to graph. So now that it's in standard form, I can graph it. My vertex of this parabola is going to be at -3, -1. -3, -1. It's going to open to the left because that guy's negative. And so if I go 1 unit up or 1 unit down, I need to go 3 units left to find the next point. And connect the dots. To a nice U shape. And I have the parabola that is the graph of that conic section. Let's do another example of graphing a conic section that is not in standard form. So for this one, if we take a look, what kind of conic section am I dealing with here? Well, notice I've got an x squared term and a y squared term, and they're the same sign. That means I'm dealing with an ellipse. Okay? So the standard form for an ellipse I have, it's x minus h squared over one number squared plus y minus k squared over another number squared equals 1. Okay? So what I want is I want everything that's not associated with x and y on one side. Okay? So I'm going to group my x's over on the left side. So I've got 2x squared minus 12x. And I'm also going to group my y's together. And I'm going to move everything else, well, this, to the other side. Okay? Now, I'm eventually going to need a 1 here, but I'm not going to deal with that yet. The first thing I want to do is I want to get these into perfect squares. Okay? And then I'll be able to divide by whatever's left so I can get a 1 on this side. Okay? So notice I have to do it twice. I have to complete the square twice. I have to do it once for my x. I need to do it once for my y because I have 2 perfect squares here. Okay? So let's do it for each. For my x and for my y, actually, I have a 2 in front of both the x squared and the y squared terms. And I need that to be a 1 in order to factor this as a perfect square. Okay? So for each of these, let's factor out that 2. And notice I'm leaving some space here so that I can add in the numbers that are going to make this a perfect square. Okay, so let's do it for each of these. So for the x term over here, it's the magic number is b over 2 squared, which in this case is negative 6 over 2. That's negative 3 squared. That's going to be 9. So I'm going to add in a 9 here. Okay. And what about what over here? Okay. Same thing. It's going to be b over 2 squared. But in this case, the b is positive 6. Also 9. But remember, I can't just add 9s willy-nilly, right? So I need to keep the equation balanced, okay? So remember, these aren't really 9s. These are really, if I were to distribute these 2s, they're really 18s. So I'm adding an 18 in here. I'm adding an 18 in here. So I need to subtract 18 for each of these. So I'm going to subtract an 18 here on this side of the equation to balance the 18 that I added here. And I'm going to subtract an 18 to balance the 18 that I added in right here. Right? That keeps the equation balanced, but it also lets me complete the square. So for this first trinomial, it's going to factor as x minus 3 squared. Remember, it's this guy before you square it. Plus 2 times, and this is going to factor as y plus 3 squared. This guy before you square it. Minus 18, that's minus 36 equals negative 18. We've done the hard part. Now we need to finish getting into the standard form of an ellipse by moving anything that's not in a square over to the other side and then dividing so we can get a 1. So I'm going to move the 36 over. 2x minus 3 squared plus 2y plus 3 squared equals. So if I add 36 to the other side, 36 minus 18 is positive 18. Okay, and then I'm going to divide the 18 both sides because I really need this to be a 1, right? So I get 2x minus 3 squared over 18 plus 2y plus 3 squared over 18 equals 1. And I do have to simplify because the numbers in front of this do have to be a 1, right? These numbers have to be a 1. So I either have to simplify or I have to rearrange so that I get a 1 up there. Anything that, if I can't just simplify these away, then I have to flip them down so they end up down here. Okay? So 2 goes into 18 9 times, so I get x minus 3 squared over 9 plus y plus 3 squared over 9 equals 1. And I have my ellipse. Okay? In fact, if you've got a sharp eye, this is actually a special kind of ellipse. It's a circle because the amount I move in the x direction and the amount I move in the y direction away from the center is the same. I'm moving 3 units left and right, and I'm moving 3 units up and down. And because I'm moving the same distance, that's a circle. Okay? And so if I want to, I could multiply that 9 to both sides of the equation over to the right-hand side. Okay? And this is the standard form of a circle with my radius squared. By the way, we could have identified earlier on that this was a circle because we get a circle whenever I have an x squared and a y squared, and they're the same sign, and they have the same number. Because I have 2x squared and 2y squared, that tells me that I'm dealing with a circle here once I finish up my whole conic section. Okay? So my center is at positive 3, negative 3. Right there, and I'm moving, my radius is 3, so 3 units up and down, 3 units left and right. So my circle looks like, let me try it one more time. Yeah, it looks like that. Let's do one more example of graphing a conic section by first putting it in standard form using the method of completing the square. Okay, so this one looks like a hairy problem, doesn't it? Big numbers, but we're going to get through it. Okay, the first thing I notice is I have an x squared and a y squared term in their opposite signs. That means I'm dealing with a hyperbola. I can't quite tell yet if this is going to open up and down or left and right. I know they're opposite signs, but which one's positive and which one's negative might flip depending on what's going on over here. Once I try to get the 1 over here, I might have a negative number, and then I'll have to divide by that negative number, and that'll flip the signs, or it might be a positive number, and I'll have to divide by that positive number, and the signs will stay the same, right? So the signs could flip or stay the same, depending on how the arithmetic shakes out. So I know it's a hyperbola, but I don't know which direction it's opening yet. Okay? I'm going to start by doing the completing the square thing, right? Remember the standard form of a hyperbola, depending on which direction it opens, x minus h squared over a squared minus y minus k squared over b squared equals 1, or y minus k squared over b squared minus x minus h squared over a squared equals 1. In either case, we need these guys to be perfect squares. So let's start with that. Okay? So let's group my x's together. Let's group my y's together. Negative 12x squared plus 24x. Now group my y's together. 27y y squared minus 162y. Leave the 123 over here for now, equals 0. Okay? So I want to complete the square for both of these. In each case, I need the leading coefficient of the trinomial to be equals 1. So I need to factor out that leading coefficient. Okay? So for this guy, that means factoring out of negative 12. That leaves me with x squared minus 2x inside. Okay? This one, I'll have to factor out that 27. Now, is 162 divisible by 27? I don't know off the top of my head. Let's figure it out. Okay? So off to the side here, we want 162 divided by 27. Okay? Now, I know 27 has a bunch of 3's in it, so I'm going to do this a little bit at a time. I want to divide 1 3 at a time. Okay? So 27 is 3 times 9. Now, does 3 go into 162? Well, it does. There's a trick, by the way. If the digits add up to a multiple of 3, then it's divisible by 3. Only works for 3's, okay? But 1 plus 6 plus 2 is 9. 9 is divisible by 3, so 162 is divisible by 3. It's going to be 3 times 54. Okay? So the 3's cancel. Now 54 divided by 9, that's a little more doable. Right? That's just 6. So it does actually go in evenly. So if I factor out that 27 from the 162, I'm going to be left with negative, don't miss the sign, negative 6y. Okay? Now I need to complete the square for both of these. So that's b over 2 squared. This b is negative 2. So that's negative 1 squared, which is 1. So I'm going to add a 1 in here into this trinomial. And that's going to complete the square. That'll allow me to factor this as I want as a perfect square. Same thing over here. B over 2 squared. This b is negative 6. So I need to add a 9 in. So y squared minus 6y plus 9. Okay. Now remember, you have to keep the equation balanced, right? I can't just add 1's and 9's willy-nilly wherever I want. The equation has to stay balanced. So I added in, not really a 1, it's really a negative 12, right? If I distribute that negative 12 in, I've just added in a negative 12. So I need to balance that. If I'm adding in a negative 12, I also have to add in a positive 12. And I'm going to do it off here to the side. I don't want it to interfere with my perfect square going on here. Okay, same thing over here. I didn't really add in a 9 here. I added 27 times 9. Okay, so if I'm adding in 27 times 9, I also have to subtract 27 times 9. And I'm lazy, so I'm not actually going to multiply that out. Okay, maybe we'll multiply it out later, but sometimes it kind of works out and it simplifies on its own. So we'll see. Okay? All right. Now these guys, the whole reason we did this is that these guys now factor as perfect squares. Okay? X squared minus 2x plus 1 factors as x minus 1 squared. Remember, this number is this guy before you square it. Okay, plus 27 times y squared minus 6y plus 9. Y squared minus 6y plus 9 is y minus 3 squared. This guy before we square it. Okay, and let's go ahead and add these numbers together. I'll go ahead and do this. 27 times 9, well, 27 is 9 times 3. 9 times 9 is 81. 81 times 3 is 243. Negative. Okay? So 123 minus 243 is going to be negative 120 plus 12 is negative 108. Okay? All right. So, we've done a lot of the work. The biggest part is always completing the square. We've completed the square. But now, we need a 1 over here on this side, on the right-hand side. So I'm going to take this negative 108, I'm going to move it over to the other side of the equation. And then I'm going to divide both sides of the equation by 108. That gives me the 1 that I need on the right-hand side. And on the left-hand side, negative 12 times x minus 1 squared over 108 plus 27 times y minus 3 squared over 108. Now remember, I need the numbers in front of these, the y minus 3 squared, the x minus 1 squared, to be 1. So I need to deal with the negative 12, I need to deal with the 27. And so what I'm going to do is I'm going to multiply top and bottom of the fraction by the reciprocal of that number. Negative 112 times negative 12 goes away. And so that leaves me just 1 on top times the x minus 1 squared over, and then on bottom I get negative, actually I'm going to leave the negative over here, negative 108 over 12. Okay, and same thing here, 1/27 top and bottom. That way I'm really multiplying by 1, right? So nothing's really changing, I'm just changing how it looks. 27's go away, leaving me just the y minus 3 squared on top. And on bottom, 1/27 times 108, it's 108 over 27 equals 1. Now I need to reduce these fractions as much as I can, okay? 108 over 12, 108 actually goes, or 12 actually goes into 108 11 times. No, 9 times. So that's just 9. But what about the 27? 108 divided by 27, that I will do off to the side. And I'm going to use the same trick. I know what goes into 27. I know what goes into 108. 3 goes into both of those. Okay. 3 goes into 108. 30. So 3 goes into 10 3 times, and 3 goes into 18 6 times. There we go, 36. And 3 goes into 27 9 times. 36 divided by 9, that also goes in evenly. It goes in 4 times. So I get y minus 3 squared over 4 equals 1. Whew! One last thing to put this really in standard form. Y minus 3 squared over 4. I'm going to put the y term first. That's the positive term. And then usually we put the negative term second. So minus x minus 1 squared over 9 equals 1. So all I did is I swapped the order of these two guys, putting the negative term second. Now this is a hyperbola in standard form, and I can graph this guy. Okay, my center is at positive 1, positive 3, right? When x is positive 1 and y is positive 3, these guys go to 0. So positive 1, positive 3 right here. Okay? In the x direction, I'm going to go out 3 units because that's the square root of 9. 1, 2, 3. 1, 2, 3. In the y direction, I'm going to go out 2 units because that's the square root of 4. 1, 2. 1, 2. Draw a box around those, and then draw your asymptotes through opposite corners of the box. And because the y is positive, it's going to open in the y direction, up and down. right? The y term's positive. So we're going to open up and down. So draw your hyperbolas hugging those asymptotes. Now, you may have been able to simplify this a little bit. You will have noticed this problem was a little bit much just because the numbers were so big. If you would have just taken a moment and look at the problem beforehand, you could have noticed that we could actually divide by something here and make the problem a little bit easier. If nothing else, we could divide by 3. 3 is usually easy to identify if everything's divisible. 12 certainly is, 27 is, 24 is. 162 is because 1 plus 6 plus 2 is 9. And since 3 divides 9, 3 divides 162. And same thing for 123. 1 plus 2 plus 3 is 6. Since 3 divides 6, 3 divides 123. So if you had started by doing that, this problem would have been a lot simpler. Okay, or at least a little simpler. So the moral of the story is do things the easy way. Okay, I've done it here the hard way, and the process worked. We got the right answer. Great. But if you had done it the easy way by simplifying your equation first, by at the very least dividing by 3, then we could have the arithmetic would have been a little easier. Before we finish off conic sections, I wanted to give you one final warning. We spent a lot of time talking about parabolas and circles and ellipses and hyperbolas, but not every equation that can be written in this form is going to be expressed as one of those standard kind of conic sections. And let me just give you a few important examples. So say both the x squared and the y squared term is 0. Well, then we'd have, maybe something like x plus y plus 1 equals 0. I'm sorry, plus 1 equals 0. Well, what's this? This would be a line. So straight lines actually are conic sections. If you take a look at that cone, right? And just have the plane just intersect just this edge right here. You'd get a line. So lines are actually conic sections. We usually don't think of them that way, but they are, right? What about something like this? Well, you might say, well, that's a hyperbola because we have the x squared, we have the y squared, they're opposite signs. But in order to meet the standard form of a hyperbola, we need a 1 over here. And there is nothing that I can do to put this in standard form and also turn that 0 into a 1. Okay? I cannot turn that 0 into a 1. This actually is not a hyperbola. This guy, if we were to move the y squared over to the other side, we have x squared equals y squared. And if I want to get rid of the squares, I could take the square root. But remember, when I take a square root, I have to think of all the possible values. So I want to think about the positives and the negatives. Okay, so this actually gives me two equations. Y equals x and y equals negative x. And so this, the solution to this is actually two lines. The line y equals x and the line y equals negative x. Okay. What about if we have something very similar, x squared plus y squared equals 1. I'm sorry, equals 0. Okay? Again, this almost looks like an ellipse, but it's not, right? Because there's no way I could turn a 0 into a 1. I can't divide by 0 to turn it into a 1, right? Because you cannot divide by 0. This actually does have a solution, although it doesn't look like it, right? Because if I move the x squared over, I get y squared equals negative x squared. Well, that means, remember, if you square something, it's always positive. So y squared is always positive. X squared is always positive, but then I multiply it by a negative, so this is always negative. So this is always positive over here. This is always negative over here. How could they ever be equal? There is one situation where they could be equal, and that's when x and y are both 0. So the only solution to this equation is the single point at the origin, 0, 0. Okay? And one last example. What if I have something like this? X squared plus y squared plus 1 equals 0. Well, if I move the 1 to the other side, I get x squared plus y squared equals negative 1. And actually, this has no solution. Okay? Because x squared plus y squared, that's the sum of two squared things. That'll always be positive. The smallest it could ever be is 0. It can never, ever be negative. Okay? So this has no solution. This can never happen. All right? So those are just some examples of what we can get with that conic section equation. And these are all conic sections, by the way. Looking at those two cones, if I take a plane that goes just vertically through the center, it'd cross these two lines, right? Those two lines would be the section that we would get. So this is a conic section. This point is a conic section also. If I take a horizontal plane that goes right through the center here, it would intersect at just a single point. So a point is a conic section. Okay? So not everything that comes from this equation is going to be a circle or ellipse or a parabola or a hyperbola. So just be cautious going forward. If you're saying x squared and y squared, it probably means you have a parabola or a circle or a ellipse or a hyperbola, but it could also be one of these other things. Okay, so just be aware of that.